Hello everyone and welcome back to yet another video from my channel Interactive Education, running for the best education possible from the student to the student for a better experience. And today we'll be going to the second part of the series on redox reactions, which is a class 11 chemistry topic of part 2. And today we're going to discuss the second part of this chapter, which is the electronic concept of redox reactions, or the modern concept of redox reactions. So in the last video, we looked at the general classical concept of redox reactions. We looked at how redox reaction is basically what? Reduction plus oxidation. So when we have reduction plus oxidation, it gives us redox reaction. So this is what we learned in the previous video. We saw that reduction has a classical definition of addition of hydrogen or an electropositive element, or removal of oxygen or an electronegative element. Oxidation was defined as the addition of oxygen or an electronegative element, or the removal of hydrogen or an electropositive element. Again, the reverse of reduction, right? And these together when took place simultaneously, which they have to, because isolated reduction and isolated oxidation are not possible. So they have to come together, and together we have a redox reaction. This is what we learned in the last video, right? So what we learned in the last video was basically the classic definition of reduction and oxidation, which has been going on for a long time. You've learned it in class 10 as well. But as time progressed, many chemists realized that the definition of reduction and oxidation based on hydrogen and oxygen, or the electronegativity of a species, the definition of reduction and oxidation based on the electronegativity of the species was not quite correct, or we can say not quite applicable in all cases. It was seen that this case could not, or this reaction could not really explain, this definition could not really explain many redox reactions. There were many redox reactions where we can't really directly see any change. It is very difficult to interpret, and in those cases also there was a redox reaction taking place, but we could not define it using these very easily. And even worse was that we could not balance these equations because they involved charge variation. And it was observed that the redox reactions involved charge variation. Right? They involved charge variation. That means the charge on both sides was not balanced, even in an equation which had balanced number of atoms, or which followed law of conservation of mass. But in redox reactions, there is charge variation. It was observed that charge is also different on both sides. And that can't be really, balanced by simply putting stoichiometric coefficients, right? So it was seen that this definition was not, completely encompassing everything which was required for a redox reaction to be studied, including balancing. Because it was seen the charges on both sides in many reactions were not same. Hence, chemists came up with the idea of the electronic concept of redox reactions based on electrons, right? And let's now look at the electronic concept. The electronic concept defines reduction as, now you have to hold your breath because reduction means gain of electrons. See, this might seem confusing. Many people do get confused. Reduction means loss. No. Reduction means gain. You'll realize why we call it reduction in just a minute. Reduction means gain of electrons. Okay. So reduction was defined as gain of electrons by an element or compound. By an element or compound. Clear? So this is how we defined reduction. Gain of electrons by an element or compound. And oxidation was defined as the exact opposite. You can guess it now. Loss of electrons, or loss of electrons by an element or compound. Right? So this is how we defined oxidation and reduction. Going away from the classical theory based on hydrogen and oxygen, and moving towards a better theory where we can actually explain charge variations also, because electrons are charged particles. If we can explain the transfer of electrons, if we can explain the movement of electrons within a reaction, we can easily explain the charge variation in that reaction also. So reduction basically meant gain of electrons, and reduction took place by gaining electrons. Oxidation took place by losing electrons. That means in a reaction, as I've told you, reduction and oxidation cannot take place isolatedly. They have to take place together. So if there is reduction, basically let's write it like this. If there is a redox reaction, so in a redox reaction, if there is element A and there is element B, now they have to both take place simultaneously, reduction and oxidation. So if element A gets oxidized, that means if element A loses electrons, if it gives electrons to the system. So if element A loses electrons, then element B has to gain electrons. That means if element A loses electrons to the system, that is, it gets oxidized, then element B needs to get reduced by gaining electrons. Clear? If A loses electrons through oxidation, B has to get reduced by gaining electrons. This was how we could explain the charge variation, because electron transfer took place. Right? That is why redox reactions are also called electron transfer reactions. They are also called electron transfer reactions because these reactions involve the transfer of electrons from one element or one reactant to the other reactant. Right? That is why we call redox reactions as electron transfer reactions. Clear with that? So reduction, this is very important for you to understand. Reduction means gain of electrons by an element or compound, which is the reactant, and oxidation means loss of electrons by an element or compound, which is again a reactant. Clear? So this was defined as the electronic concept of redox reactions. Now, this concept really cleared a lot of our minds. It made us a bit free with regards to redox reactions. We were stuck to a classical theory, but the introduction of the electronic theory broadened our minds and our approach towards the redox reaction. So now we are going to look at a new concept which scientists came up after the electronic theory. So after the electronic theory came into being, scientists began coming up with the idea of bringing in a particular kind of special number. Okay? They thought of bringing a number. And that number would denote the charge on a particular element or atom or sometimes group of atoms in a particular redox reaction. And that would help us in studying charge variation per element or atom. Charge variation per element or atom. Per element or atom we could study charge variation, and using this very special number which would help us in determining charge variation in particular atom, elements and compounds. Not compounds exactly, but groups of atoms or atoms. This number was referred to as the oxidation number. Right? And very interchangeably we use the term oxidation state. Clear? So they came up with the idea of oxidation number or state, oxidation state, which would help us in determining charge variation per element or atom in a given atom or group of atoms involved in a redox reaction. Right? And oxidation number is basically defined as, basically we defined oxidation number as a charge, real or imaginary. Now this could be either real charge or imaginary charge. See, you know that many compounds are neutral, right? Still we calculate oxidation numbers of atoms in that neutral compound also. So that means there the charge doesn't really exist, right? It's because of a partial charges in the structure, because of electronegativity difference between bonds, that we are able to come up with this imaginary charge. But in some particles such as ions, polyatomic or monoatomic ions, the charge is real because they have lost or gained electrons, right? So in that case, that real charge will be the oxidation number. But in the imaginary case, there are some rules we'll need to follow, which we will study just a bit, just a bit. So oxidation number is a charge which is real or imaginary on an atom, element, group of atoms, or ion involved in a redox reaction. Involved in a redox reaction. So it is a charge which is real or imaginary on an atom, element, group of atoms, or ions involved in a redox reaction. Clear with this? It's a very, very important concept. You must understand it. So here you will realize that this charge or imaginary charge or real charge on an atom or group of atoms or ions will help us in studying charge variation. It will help us in studying how charge will vary from one side to the other side, and this is very, very important now, right? So let us now look at the set of rules by which we can determine oxidation numbers of different atoms, of different elements in various redox reactions. And once you're thorough with these rules, your redox reactions become very simple. It is very easy to balance reactions, very easy to understand reactions, because this oxidation number concept helps us in understanding reduction and oxidation. Because again, electron transfer always, basically this is a conclusion of electron transfer only. Clear? So let us first learn how to determine oxidation number in various cases. Let's just list down the rules. Very simple rules, right? The first rule, so rules for writing oxidation number, right? Very simple rules, to the point, clear and concise. Now rules for writing oxidation number. The first rule and foremost rule is that for atoms or elements in free state, the oxidation number is equal to 0. Clear? So what do we mean by free state, or what do we mean by ground state, all these things? For example, hydrogen, H2, hydrogen molecule, okay, not atom, it can't exist in atomic form in nature. So H2, which is the free state of hydrogen gas, in this case, in this H2 molecule, the oxidation number of hydrogen, please remember we calculate oxidation number or oxidation state per atom, right? So oxidation number for hydrogen in this case is 0. Oxidation number for hydrogen is 0. Why? Because here hydrogen is in diatomic form in its free state, not in combined state, right? In free state as a molecule, diatomic molecule, dihydrogen. So here the oxidation number of hydrogen, which is per atom, is 0. Another example is oxygen. Again, very simple. In this case also, the oxidation number of oxygen is 0. If we take the example of phosphorus in P4 state, again, ground state, free state, so oxidation number is 0. Sulfur, S8, again in its free state, so oxidation number of sulfur is 0. So these are different cases. In any case where you will find it in the ground state, the oxidation number will be 0. Now why is this so? Let's study this also. See, if you take any of these, let me take hydrogen since it's the simplest to understand. Hydrogen, if you look into the structure, it is basically two hydrogen atoms attached through a covalent bond, right? Two hydrogen atoms attached through a covalent bond. Now in hydrogen molecule, two hydrogen atoms attached by a covalent bond, and both the hydrogen atoms have same electronegativity, right? Can you say that one hydrogen is more electronegative? Obviously not. So both hydrogen atoms have same electronegativity. As a result, this bond between them is a non-polar bond. It is a non-polar bond. And you know, if a bond is non-polar, then there will be no partial charges. That means electrons will not shift towards one atom in particular. They will be centrally placed in the molecular orbitals. That is why here there is no partial charge or no shifting of electrons towards one center. Hence, the bond is non-polar. Clear? And in this way, you can explain oxygen also, you can explain phosphorus also, you can explain sulfur also. In all cases, the non-polar bond is the reason why there is no partial charge between atoms, and hence they have zero oxidation state. Clear? Next, let's come to the second rule. The second rule will be that for fluorine, this is a very important rule, that's why it has come at the second level. For fluorine, fluorine is the most electronegative element in periodic table. You know that, right? So that's why it's a special case. For fluorine, oxidation number is always, never will it be different. Always. For fluorine, oxidation number is equal to, in all cases, -1 in combined state. In combined state. Okay. So whenever fluorine is present in a compound with another atom of different electronegativity, then the oxidation number of fluorine will be -1. If it's F2, it is still 0, because here also fluorine-fluorine bond is non-polar, electronegativities are same. But in combined state, fluorine will always have -1 oxidation state. For example, HF, hydrogen fluoride. Hydrogen fluoride has a single covalent bond between hydrogen and oxygen. Hydrogen being more electropositive and fluorine being obviously the most electronegative element of the periodic table, gets a partial negative charge, and this hydrogen gets a partial positive charge. So because of this partial negative charge, since only 1 unit of partial negative charge is present, the fluorine gets -1 oxidation state, and hydrogen here will get +1 oxidation state. Clear? So understood how we are getting this? This partial charge is minus delta. Minus delta denotes partial charge, means it's not real. It is imaginary, because you know HF is what? It is a covalent molecule, right? That is why. Understood? So HF is a covalent neutral molecule. So hydrogen has partial positive charge, only 1 unit of partial positive charge, so +1, and fluorine has 1 unit of partial negative charge, so -1 oxidation state. Together they will form 0. Clear? So in all cases, for fluorine in combined state, oxidation number of fluorine is -1. Number 3, let's come to our favorite element, hydrogen. So for hydrogen, we have 3 cases, right? 3 cases for hydrogen. First case is in free state, H2 form. So in free state, oxidation number for hydrogen is 0. Obviously for any element it is 0. Second is in its non-metallic hydride. In its non-metallic hydride. What do we mean by non-metallic hydride? Basically any compound of hydrogen where hydrogen is present with a non-metal, right? Any compound of hydrogen where hydrogen is present with a non-metal, right? That is called a non-metallic hydride. So in such cases, oxidation number, now you know non-metals are usually considered electronegative elements. So in that case, hydrogen will exhibit its electropositive character, and oxidation number of hydrogen will be +1, because it conveniently can lose 1 electron and form H+ ion, right? Clear? Next is in metallic hydride. In metallic hydride. Metallic hydride means that hydrogen is present with a metal, right? So obviously you know metals are considered very strongly electropositive elements, and hydrogen in that case will exhibit its electronegative character, because hydrogen can act as both halogen and group 1 alkali metal. So in metallic hydride, it will exhibit its electronegative character, and the oxidation number of hydrogen will be, can you guess? Yes, it is -1. Clear? So for hydrogen in free state, oxidation number is 0, that is in H2 state. For a non-metallic hydride, oxidation number of hydrogen is +1. You can get an example very simply. For example, HF only. See here, F is non-metal and highly electronegative, and hydrogen here will exhibit its electropositive character. The oxidation number of hydrogen will be +1, right? You can take another example. For example, water molecule. Now in water molecule, if you draw the structure, oxygen forms two covalent bonds with hydrogen, and there is bent structure, 104.5 degrees angle. Now, here you can see oxygen is more electronegative than hydrogen and it's a non-metal. So electrons will tend to shift here, and with this particular bond, it will get a partial negative charge, and this hydrogen will get a partial positive charge. So 1 unit of partial positive charge and 1 unit of partial negative charge for oxygen. Similarly, in this partial positive charge for hydrogen and another unit of partial negative charge for oxygen. So hydrogen will get a partial positive charge of 1 unit per atom, and you'll get an oxidation number of +1. On the other hand, if you look at oxygen, which we will discuss just after this, you have 2 units of partial negative charge, right? 2 units of partial negative charge. So the oxidation number of oxygen will become, can you guess? Yes, it will be -2. Clear? So here you can see non-metallic hydride how hydrogen will get a +1 oxidation number or oxidation state. In a metallic hydride, it has -1 because there it exhibits its electronegative character. For example, NF means sodium fluoride. Sorry, excuse me, not NAF, NaH, sodium hydride. And now, if you look at NaH, sodium forms an ionic bond. Sodium forms an ionic bond with a hydrogen atom. This hydrogen atom obviously will show its -1 state by gaining 1 electron and forming ionic bond with sodium, and sodium here in every case will exhibit +1 oxidation state because sodium is a very strong electropositive metal, that is element. So obviously here hydrogen will exhibit -1 oxidation state because metals are very electropositive. Clear? Especially sodium being an alkali metal, the most electropositive. Clear? That's it. So that is for hydrogen. Next, let's learn another rule in general for a particular kind of metal. Now you know metals are electropositive elements in general. So for two very special groups of metals, we have fixed oxidation numbers. You know, if you look at D block elements, right? D block elements will exhibit variable oxidation number. For example, zinc. Zinc can exhibit +2 and +3. Iron, Fe, can exhibit +2 and +3. Copper can exhibit +1 and +2. Mercury can exhibit +1 and +2. So these are D block elements and they exhibit variable oxidation states. Clear? Now for the fourth rule, if we see metals of group 1 and group 2 elements, alkali metals and alkaline earth metals, that is the lithium group and the beryllium group. These two have fixed oxidation numbers because they don't show variable valencies, variable oxidation numbers, right? So for alkali metals, that is group 1 elements, the oxidation number is always equal to +1 in combined state. See, for metals, always positive oxidation state in most cases, right? Then for alkaline earth metals, that is the calcium group, okay? Alkaline earth metals, that is group 2, oxidation number is equal to +2 in combined state. Clear? Because alkaline earth metals have 2 electrons in their valence shells. They can easily lose those 2 electrons and form a +2 oxidation state. Similarly, alkali metals have 1 electron in their valence shell. They can easily lose that 1 electron and form a +1 oxidation state. Clear? So that is what we call alkali metals or alkaline earth metals. Clear? That is their oxidation state. Yeah, so what are the alkali metals? Sodium, we can just list them down here. Lithium, sodium, potassium, rubidium, cesium. Francium is also there, but it is considered electronegative. We don't know much about it. Because its half-life period is very short. For francium, half-life period is very short, hence we don't know much about it. You learn more about it in S block elements. Alkaline earth metals, basically they include beryllium, magnesium, calcium, strontium and barium. Clear? Calcium, strontium and barium. These are the alkaline earth metals. Clear? Now let's come to the fifth and last rule for this particular video, where we're going to discuss the fifth rule, which is based on oxygen. Now oxygen, one of the most fascinating elements with regards to oxidation number. Now oxygen in general, oxidation number of oxygen in its compounds, in general, please make sure you read this well. In general means there are some exceptions. Oxidation number of oxygen in its compounds is -2. Is -2. In most of its compounds, you will find that oxygen has an oxidation number of -2, right? But there are exceptions. So let's write down the exceptions, because exceptions are the favorite concepts or favorite part of examiners, right? They always want to put the exceptions, especially JEE, joint entrance examinations and other competitive exams, Olympiads. We'll always see, even my teachers tell me, exceptions are their favorites. So if you look at the exceptions, the first exception is with regards to its peroxide. This is the most prominent exception, and this is very important because if you understand this, in many compounds it has applications. Peroxide linkage. Now usually you know that oxygen has a double bond with oxygen in its, in general, in its normal molecule, O2 molecule, it has a double bond with another oxygen molecule. But in many cases you will see that oxygen atom forms one bond, single covalent bond with another oxygen atom, and their other bonds are with other atoms. Clear? Their other bonds are with other atoms. In this case, this bond makes them acquire partial negative charges. Okay, these other bonds make them acquire partial negative charges, and each of them have partial negative charges, 1 unit each of partial negative charge, because the central bond does not provide any polarity to any of the atoms because it is a non-polar bond. So they each gain partial negative charge units, 1 partial negative charge units from their other bonds if the bond is polar. And in this case, we get basically O2 -2. We get a case of 2 oxygen atoms with a total charge of -2 units. So each oxygen atom gets an oxidation number of -2. No, it's -1. Because two atoms in a molecule with -2 on the whole molecule. So per atom is -1. So in peroxide linkage, this linkage is called peroxide linkage. It is called peroxide linkage, and in peroxide, the oxidation number of oxygen is equal to -1. Clear? It is equal to -1. Clear? So this is the first exception, peroxide linkage. The second exception is the compounds with fluorine. Compounds with fluorine. Now you know fluorine is the most electronegative element of periodic table, right? Is it more electronegative than oxygen? Yes, it is more electronegative than oxygen. So if you find a molecule containing fluorine and oxygen only, you will see that fluorine will get the partial negative charge and oxygen will in turn exhibit partial positive charge, despite being the second most electronegative element in periodic table, right? But why does it exhibit this partial positive charge or this oxidation number of positive oxidation number? It's because there fluorine will dominate its electronegative character. So if you see compounds of fluorine with oxygen, there are only 2 compounds of fluorine with oxygen, F2O and F2O2. Only these 2 compounds are there where oxygen and fluorine are present together. And in each of these compounds, if you draw their structure, oxygen, right, forms 1 bond with fluorine, 1 bond with fluorine. This is your F2O. So in F2O, 1 bond with fluorine, 1 bond with fluorine. Here you will see that between F and O, which is more electronegative? Fluorine. So fluorine will get a partial negative charge, oxygen will get a partial positive charge. Fluorine will get a partial negative charge, oxygen will get a partial positive charge. Now, what will be the oxidation number of oxygen here? Right? Now you know the oxidation number of fluorine will be -1. So -2, and then here this oxygen will get an oxidation number of +2. Clear? +2, because 2 units of partial positive charge. Clear? So here you can see oxygen, being the second most electronegative element, still has positive oxidation number in the presence of the highest electronegative element, fluorine. Next, come to F2O2. In F2O2, if you see, fluorine forms one bond with O, then this O forms another bond with another oxygen atom, and this forms another bond here. So check the polarities of the molecules. There is a peroxide linkage, right? So here you have a partial negative charge, here you have partial positive charge, here you have partial positive charge, here you have partial negative charge. So this is a peroxide linkage, non-polar. So each oxygen atom has an oxidation number of +1. Clear? So only in F2O and F2O2, where fluorine and oxygen are present together, oxygen will exhibit partial positive character. In no other case will it exhibit partial positive character. Clear? Partial positive charge or positive oxidation number. The third exception, if you see, is that of oxygen can also exhibit a new kind of linkage, right? And that is called O3- linkage. This O3- linkage is called ozonide. Okay, ozonide. Ozonide, you will see that the oxidation number of oxygen is -1/3. Oxidation number of oxygen is -1/3. Clear? So this is another case of exception in case of oxygen, that is ozonide, where oxygen has an oxidation number of -1/3. This is a very rare case. Okay, I have never seen ozonide being very prominently used, but just in case it comes there, I'm just telling you about it, right? So that is for ozonide, right? And there's one last exception, which is superoxide. And superoxides are a special kind of compound, and they are formed only by 3 elements in the periodic table. Total 3 elements with high electropositivity, which are potassium, rubidium, and cesium. Only these 3 elements can form superoxides because they are highly electropositive elements. And if we denote them to be M, then the formula of a superoxide is MO2. MO2. In general, you expect an alkali metal to form an oxide of form M2O. But because potassium, rubidium, and cesium are very highly electropositive elements, strong metals, some of the strongest metals in the periodic table, because of that reason, they can't form a normal oxide and they form superoxides, right? So they form compounds like KO2, RbO2, and CSO2, right? Clear? Now I've told you already that alkali metals always have +1 oxidation state in all their compounds, right? So in each of them, it will have +1 oxidation state, right? Now in total, for a neutral molecule, total oxidation number should be 0. You can guess that, right? There should be no charge. So basically here, if you equate that, so if you take the oxidation number of O to be X here, so 1 plus 2 times of X, because as I've told you, it is always calculated per molecule. So 1 plus 2X is equal to 0. So what will it imply? X is equal to -1/2. This is the oxidation number of oxygen in a superoxide. In a superoxide, oxidation number of oxygen is -1/2. And superoxides are only formed by three elements in the periodic table: potassium, rubidium, and cesium. And oxidation number of oxygen in a superoxide will be -1/2. Clear? So there are four exceptions, right? Peroxide in them is the most important. We will in the coming videos study about the ranges of oxidation number of specific elements or of different elements. If in a compound you follow the general method taking oxygen as -2 and you get an oxidation number of the required atom which is different from its range, which is out of its range, then you can be dead sure that there is a peroxide linkage. There is some exception there, right? That is where these exceptions help us, especially peroxide, because peroxide is applicable in a lot of cases. Compounds with fluorine, only two are there. Ozonide is very, very rare, and superoxide are only 3 cases. So you can see here the exceptions are less, but this peroxide is present in a lot of compounds. So that is why this peroxide is the most important, because it can help us determine exceptions more prominently. Clear? So these are the 3 exceptions of oxygen, 4 exceptions of oxygen, excuse me: peroxide, compounds with fluorine, oxygen in the form of ozonide, and superoxides. Clear? And with this, we conclude this video on oxidation number part 1. In the next video, we will be continuing with the rules of oxidation number, where I will discuss the coming rules or the next rules of oxidation number. So thank you very much for joining me. Do like and subscribe. If you have any kind of doubt, please welcome in the comment section below. Any suggestions, also welcome in the comment section below. Good luck for your examinations, if any, and thank you very much for joining me. Do like and subscribe, tell others about the channel, and thank you very much.